So day 115 goes over the calculus sides of parametrics, and the first thing we start with is the chain rule. So if we're going to use parametrics to describe motion in an xy plane, then we'd like to know what the rate of change is, so we need y prime. Y prime is defined as dy dx, but since we have this third variable, we're going to now include dy dx and expand it out to say dy dt times dt dx would produce dy dx. That's the same thing as flipping the second fraction and saying dy dt divided by dx dt is y prime. So the rate of change of y with respect to t divided by the rate of change of x with respect to t is the first derivative. The second derivative has a little bit of a wrinkle to it because the second derivative is defined as the first derivative of y with respect to x. So dy prime with respect to t divided by dx dt. So what we're going to do is we're going to take the second derivative, or the derivative of the first derivative, and then divide that by dx dt again. That's a little bit strange. It's not just the second derivative of y divided by the second derivative of x, all with respect to t. So you got to be a little bit careful with this formula here. So as an example, suppose a particle is moving according to this function in the x direction and this function in the y direction. And we want the first and second derivatives, eliminate the parameter, sketch, and find the slope at t equals 0. So first derivative is pretty straightforward. Find dy dt, find dx dt, and then divide those. So 2e to the 2t divided by negative e to the negative t produces negative 2e to the 3t. Second derivative, again, is the first derivative, the derivative of the first derivative. So we're going to take the first derivative divided by the first derivative with respect to x. So the derivative of the first derivative becomes negative 6e to the 3t. I'm going to divide that by dx dt, which is negative e to the negative t. And this time, again, we get 6e to the 4t. Eliminating the parameter, since I see e to the negative t, I'm going to attempt to substitute that in here. So I'm going to take e to the 2t and rewrite it as e to the negative t raised to the negative 2. E to the negative t is x, and I've got x to the negative 2, which is the same thing as 1 over x squared. To find the domains, t can be anything. Both of these functions are exponential functions, so their output can only be positive. So both x and y will only have positive outputs. That makes sense and agrees with the shape of y equals 1 over x squared. Both the x and y values remain in the first quadrant only. And finally, what's the slope at t equals 0? If I substitute in 0 to the first derivative equation, dy dx, I get negative 2. And again, looking at the picture at t equals 0, I have the ordered pair 1, 1. And it looks like the slope of the tangent line at 1, 1 for 1 over x squared is indeed down to right 1. Second example, we have another relationship with trig functions and x and y. So to find horizontal and vertical tangents, we're going to find a function for the slope and then use the numerator and denominator separately. So again, the slope, or the first derivative, is dy dt divided by dx dt. dy dt is cosine theta, dx dt is a negative 3 sine theta. So setting up a fraction, a horizontal tangent is when the slope equals 0, so the numerator must equal 0. Cosine theta equals 0 at pi over 2 plus pi k. And then the slope is undefined when the denominator equals 0, and that's true when theta equals 0 plus pi k. So I can get the coordinates of the location for the horizontal and vertical tangents by plugging in pi over 2 and 0 and their increments in this table over here. Starting at 0, when I plug in 0 to these two equations, I wind up with 8 and negative 2. Cosine of 0 is 1, 5 plus 3 is 8. And the sine of 0 is 0, so I get a negative 2. So at the point 8, negative 2, I'm expecting a vertical tangent. The next location of a vertical tangent is at pi. Again, plugging in pi. This time, cosine of pi is negative 1, so 5 plus a negative 3 is 2. And sine of pi is 0, so again, I get negative 2. At 2, negative 2, I'll have a vertical tangent. So the vertical tangents are here. Same process for the horizontal tangents. Start at pi over 2. And 3 pi over 2, plug into the equations, you get the ordered pairs 5, negative 1, and 5, negative 3. And those values make sense. At 5, negative 1, we have a horizontal tangent. At 5, negative 3, we have a horizontal tangent. At 8, negative 2, we have a vertical tangent. And at 2, negative 2, we have a vertical tangent. Last example involves finding arc length. So this was our old formula for arc length, the antiderivative of 1 plus f prime of x squared dx, that should be, not dt, dx. And the f prime of x is dy dx. So now we're going to take and expand our dy dx to include dt's, and instead of leaving it as a fraction, we're going to undo something that we saw in the proof for this and change this 1 plus f prime of x squared into dx dt squared plus dy dt squared, this time with the correct dt. So again, two functions based on trig, two parametric functions based on trig. Dx dt squared is right here. Derivative of t plus sine t is 1 minus cosine t. Dy dt is right here, sine t. Squaring all that out and combining, I get something that's not real helpful right now. So we got to do a little bit of a trig identity trick. 2 times parentheses 1 plus 1 minus cosine t is going to be changed into 4 on the outside, 1 minus cosine t over 2. The reason why I want this 4 and this 2 here is because now 1 minus cosine t over 2 is the half angle identity. If I take 1 minus cosine t over 2 square rooted, that's the same thing as sine of that half angle. So the square root of 4 becomes a 2, which moves to the outside. And now I have the antiderivative of sine t over 2 dt. Doing a u substitution, I needed a 1/2 dt. So when I put the 1/2 dt in here, I need to offset that with a 2 on the outside. So one of the 2's came from the square root of 4 that I needed to get the trig identity formula. And the other 2 comes from the u substitution. So now I have 4 antiderivative of sine, which is negative cosine. Substituting in values of 2 pi and 0 into this function, I'm going to get 1, positive 1, and then a negative 1. The difference between 1 and a negative 1 is 2 times 4 is 8. 8. So the length of this arc is a nice, neat 8.